Um, our first speaker is Ivan Titov, who is faculty at the University of Edinburgh and also Amsterdam, and works at the intersection of like NLP, LLMs, and other interesting things. So take it away.
Okay, thank you very much. So yes, I will be giving a talk about AI safety and LLMs. And I should, from the start, say that I and my group is new to the safety area, but we have been doing for many years work which is related, I believe, to safety. For example, consider Nicholas Decal work on editing language models, so basically the earliest work on parametric editing, or Lena Voigt's work on interpreting, discovering modularity in transformer models. So this is, of course, a very ancient work by the standards of our field, but we continued working on these topics, on unlearning, on influence functions, interpretability. And excellent example here is work of Verna Dankers on memorization. She takes a very different perspective, not a safety perspective no memorization, but I think we all agree that understanding memorization is very relevant to making models safe. And Verna is now here in the audience and a postdoc in Siva's group at Milan. Okay, today I'm not going to talk about things which are slightly related to safety. I'll talk actually about research directly in safety in AI, and we'll look into two topics. First, we'll discuss faithfulness of chains of thoughts. So why chains of thoughts may be not faithfulness. We'll look in specific scenarios and also try to mitigate, see how we can fix post-training to reduce unfaithfulness. And in the second part, I will actually start with a motivation which is similar to Yov Artsy's motivation if you were yesterday in the talks. So the risks connected with all the information flowing to a few entities. Whereas Yov's solution to this was trying to develop a small controllable model, we will try to make AI agents to stick to privacy constraints, and we will see how this works. So let's start with chains of thought and faithfulness. So this is work of Pedro Ferreira, my student in Amsterdam. Yes, indeed, my group is split between two locations. We can discuss later how this works. And also this collaboration with my colleague in Amsterdam and a good friend, Wilke Razis. So earlier, we engineered models for interpretability. So, for example, integrated interpretable layers into models. Many of you may know concept bottleneck models, where you add between your perception model and a classifier on top, you add a bottleneck of interpretable concepts. So they had this interpretability embedded inside the models. And it's not like I'm honestly arguing that we shouldn't look into interpretable narrow-symbolic layers. I believe there are many reasons to still look into this, and we yesterday listened to Pariza and also to Bo, which were making very good cases for why using narrow-symbolic reasoning can be good from providing certain guarantees, robustness. So there are many reasons, but we don't have to, right? So now we have chains of thoughts. We have this reasoning traces of language models in the output space. The problem is that chains of thoughts are not necessarily faithful to model reasoning. And this is well documented. There are a number of papers in the last couple of years showing different types of unfaithfulness and looking at different metrics of unfaithfulness. And of course, this is not great, and we should be looking into ways to improve faithfulness of chains and also kind of monitor the way we modify our post-training algorithms so that we don't lose this window into model reasoning, or maybe handle a model reasoning, because to a certain degree we can intervene on these chains. Also, as a side note, these interpretable layers we used to work and still work, and used it's more about my group. We used to do a lot of work on integrating differentiable reasoning layers in the models. But they're also not necessarily so interpretable, right? So they don't guarantee faithfulness. They're also not perfect, and not to mention the post hoc interpretability. So in a way, chains of thoughts are great, they're simple, they're already there, and they are not necessarily weaker than potentially more complex alternatives we can have. So that's why I think the very important question is to understand what drives unfaithfulness in chains of thought, and to think how we can mitigate that. And just not to be very abstract, let's look in a specific scenario. So I played with GPT-4 a few months ago, and so the idea here is a CV screening application. So I know the CV screening is a bit of scary from ethics perspective, but for example, in Amsterdam, there is a fairly big company, and this is the focus of this company is automating recruitment. So whatever we think about these things, this is happening all the time, right? And to make it a little bit of more fun and also more controlled, we are not just we'll look into real CV screening, we'll look into recruiting a squad of fantasy animals for some intellectual game. And the setup is very simple, very standard. So we have a prompt defining the context of the task, so what needs to be done. And then there is a list of CVs of animals, and the LLM should predict select one or several CVs. And what we do in the prompt, don't look in the details of the prompt, not much is actually very interesting there, but what is crucial is that we create a certain conflict between what is perceived by LLM as effective reasoning. So we mentioned previous statistics. So we mentioned that animals from some made-up location island were very successful. And we also emphasize that selection should be fair and merit-based. So there is a conflict. And you may argue this is quite artificial, but actually there are many cases where there will be certain conflicts between some cues in the output about what's sufficient and what you can actually justify. So it's really very clear here, but we will see also examples where this conflict is maybe more hidden with biases and so on. Then how do we generate CVs? So these animals, one animal is from this queued location, from a made-up location happened to be very successful in the past. And then the other attributes of these animals actually unrelated to intellectual games. So it's specifically created in such a way that the CVs are terrible. There is nothing useful for LLM to actually rely on. So this is all about appearance, about physical strengths, nothing about anything related to the intellectual abilities. And what happens, I think you can already guess what happens when we provide it to LLM. It reliably selects this one animal from island, and then it fabricates lots of reasons for this, not mentioning actually the location. And then it goes even further, that actually tells you that it based this decision on traits alone, whereas actually the characteristics of these animals are completely randomized and not related. So it's clearly fabricating the reasons for making this biased recommendation. Okay, so now we see one example of this problem with nearly state-of-the-art models. So this is not GPT-5, this is GPT-4. So one question we could ask, which training stages are to blame for this behavior? And I think the answers usually will be fairly complex, so many of them are probably to blame. So it's naturally pre-training, instruction tuning with SFT would contribute to this. Right? The humans are not always sincere in their reasoning. Annotators are not always careful and also follow certain shortcuts. So no doubt these stages contribute, but in this talk I will discuss how post-training with preference learning algorithms like DPO or reinforcement learning algorithms can contribute to this behavior and amplify fabrications. So now let's look at the even more controlled setup, which will allow us to measure everything very carefully. So this is what I call a mass cheating problem. So we give an LLM a mass task and also a textbook, pretending that it can learn from this textbook. But this textbook may leak the information. So it may contain, and in our test sets will contain already solution to this problem. And we tell LLM not to rely on this solution, or if it relied on this, to acknowledge the reliance on the solution. Then the way we will be training the model will be using a reward model, and the reward model will have access not only to the answer, but as well to the reasoning chain of the model. And what we can see here, we can see again that this setting incentivizes the model to hide that it was using the solution from the textbook. So it's very easy if you look into this distribution of reward scores. So the blue part is distribution of reward scores for incorrect generations. Naturally, the score is low. Then you have green and red, which correspond to the correct answers. But the green ones are the ones where the model acknowledges that it relied on a solution in a textbook, and a red one, it didn't. So you can see that by just hiding this acknowledgement, and this also usually means that you need to fabricate the way you solve the problem, pretend that you solve it by itself. And by hiding, you effectively gain in a reward score. So it's very natural that this is what the generator in this situation is learning to do. It's learning to hide. Okay, so let's look a little bit in the numbers and what is happening. So let's start with the model. Actually, I call on this slide it a base model, but it's actually here the results of instruction tuned model. So no training, it's just pre-trained model, no training on this data set for now. And mass book is what we just discussed, and bias QA is a version of a winner-generated data set from Paris et al. So it's in many ways, it's kind of similar to what we discussed before this CV setting. So it exploits the bias of the model. And so what we measure is some measure of unfaithfulness. We can actually discuss whether this is a perfect measure, and we in the paper look in different ways to actually detect unfaithfulness. But what we do here on this slide is very simple. So we have multiple runs with solution and without solution, and we see the gain the model gets from having access to the solution. And we deduct from this the percentage of generations with a solution where a model acknowledges the use of the solution. So this is done with a LLM model. We detect the acknowledgement. And you can see that already the model we start with is actually not very good. And this is not surprised, right? It's related, surprising that's related to what we already saw on a slide with GPT-4o. And then here we look into online DPO for training, and with two different reward models. And what we can see is that in most of the cases, this unfaithfulness increases, right? So in both cases, in mass book and in one of the cases with bias k. Of course, it gives us insights that some of the reward models in certain situations may actually be more robust in detecting unfaithfulness. For example, for mathematics, sometimes a reasoning model can detect that the chain doesn't make sense because the weaker model makes up a reasoning which is broken, right? So this indicates that something is not very good in this chain, and it gets still a low reward score. Now, what do we propose? We discussed that the issue with this cheating is because reward model has only access to the reasoning chains and the answer. It doesn't have an access to internal reasoning of the model, so what model is actually doing. And so what we're trying to do here is to provide to reward model access to the internal reasoning. And one way to do this would have been to use an interpretability techniques, and I'll later discuss why I think it's not such a great idea. So instead here, what we do, we generate counterfactuals in training. So similarly to how we were evaluating faithfulness or unfaithfulness on the previous slide, here we will be, during training, we will be generating counterfactual, which is, in this case would correspond to removing this solution from the prompt and recording the answer. And if the answer switched or became incorrect, then what we do, we simply add an extra acknowledgement to the generation of the model. So we just add this, that I acknowledge that I basically relied on the solutions that I cheated in providing this response. So these tags, even though they're noisy, so that's one of the issues with this, because we can't afford running many generations, they incentivize the model to actually cheat, because if you still will be revealed that you will get this tag, most probably, if you cheated, then there is no reason to cheat. So this is basically the idea we exploit here. And now, before looking into actually preference learning, let's look what's happened with the best of n. So in this case, we are not training anything, right? We just use a pre-trained model and select the top rewarded generation according to the reward model. So A is the reward model in a normal setup, or when we're using these disclosure markers created the way I discussed on the previous slide. And so what you can see that unfaithfulness, where is my cursor? Anyway, okay, that's here. So you can see that unfaithfulness is much lower. It doesn't grow that fast with this approach. And this is also across the data sets and across the reward models. Now let's look what is happening when you're actually training using this algorithm, again, on the same two data sets. And results here are not as perfect as I would like them to see, but still we see a consistent drop in unfaithfulness across the data sets and across the reward models. So providing this tag appears very useful. So what I want to say is that this is, of course, a proof of concepts, and there are a number of limitations to this idea. So the first, we here use a heuristic process for generating counterfactuals. But in principle, in other contexts of interpretability monitoring, there's been work on generating counterfactuals. For example, Kate Matten paper at ICLEA this year. There are all extra expenses to this process because you need to run extra forward or extra rollouts to actually add these attribution tags. But likely this is possible to do not all the time. So you need to basically, you can monitor unfaithfulness and vary the rate of generating of this, but we didn't experiment with this yet. And of course, these data sets we looked into, they had this conflict between efficiency and what is kind of reasonable, what is allowed type of reasoning, right, legal reasoning. So not all examples will have this property. So detecting examples where this is relevant, I think it's a big question, and being able to detect these examples can be relevant to many other things, also to data filtering, to augmenting data for training reward models, and as well for running our approach selectively. So why are we using counterfactuals are not using attribution techniques? Because in principle, it may have been cheaper than running these rollouts. And for this, I want to mention a earlier work by the same student, by Pedro Ferreira. And maybe you're familiar with this or not, but there was for a couple of years ago in NLP a trend to try to guide language models with a human rationale. So you have annotation from the user, why they assigned certain label or made certain predictions, and a number of papers tried to regularize attention or attribution scores towards these labels. And what Pedro did, he analyzed what is actually happening in these techniques. And what we realized that actually not much is happening in terms of actually changing the model behavior or even robustness of the model. But what was obviously happening, it was they were hacking the interpretability techniques. And there are lots of analysis in this paper. It's a bit of kind of paper written out of frustration, I would say. But I think this is one very intuitive illustration. So here, we take two attribution techniques, two recent, assumed to be very strong attribution techniques, ALTI and attention rollout. And when you measure agreement on a model which is not trained or trained without a guidance, you see very high agreement between them. So they're pointing to the same things. But when you start to guide with one of them, with attention rollout, I believe, this correlation completely disappears. So it figures out how to locally cheat attention rollout without shifting other interpretability techniques. So instead of actually genuinely changing behavior, it managed to hack. So counterfactuals, if they're generated in a good counterfactuals, there are a few caveats here, harder to hack. Okay, so this is it for this first part of my talk. And what I was arguing is the chains of thoughts are crucial and very important for AI safety. And we shouldn't be overly puristic as well, because nothing is entirely faithful, right? And we still find this useful. So when you talk and debate with the people, we don't necessarily know that the arguments are faithful for what they actually think, right? But we still find these debates useful. So similarly with agents, we shouldn't necessarily require that chains of thoughts are entirely faithful, but they should have to do something with the reasoning. And so it's important to us to think how we preserve that. And we discuss one of the ways of trying to do this. Okay, oops. Now let's switch gears and look into private collaboration between large language models. And this is the work of Guillem Ramirez, this time a student from Edinburgh, and a collaboration with Alexander Birch, who is faculty in Edinburgh. So the motivation here, as I already mentioned, is very similar to Yov's motivation. So there are many risks connected with the current practice. Current practice, I mean that all the data from the user flows to very few entities. So there are privacy risks, there are safety risks of this being hacked, as Yov mentioned, power concentration, dependency, and so on. So this is perhaps not great. But I also think that full isolation, that you will have autonomous LLMs running on a user side, is unrealistic. because there always will be stronger models stronger in certain capabilities. So you would want still these local models to collaborate with remote models to improve on their behavior. Otherwise, you pay a big cost of using weaker models. And so what we propose here is to give users control on what they're happy to share, or maybe happy is the wrong word, okay to share, and what they absolutely don't want to share with remote systems. And given these constraints, which we can call contracts, we call them privacy profiles in this case, because they're kind of too simple to call them contracts. So our goal is to maximize utility of collaboration with remote system while respecting this privacy constraint. So first, maybe let's discuss what is private. So what should be preserved? And kind of classic approach to this would be we remove PI, personal identifiable information. But of course, this is not really what you want. Not only what you want to protect, right? You may want to protect political views, unfortunately, it's becoming more and more relevant these days, right? Health concerns, private relations, and so on. And to maybe let's have a look actually in data which is real or kind of similarly real. I adapted with Guillaume, we adapted a couple of examples here. And if these are examples from a wildchat data set, maybe you know about this data set. It was collected from the users who agreed to share their data in exchange for having access to OpenAI models which are otherwise commercial. And so what you can see if you just hide named entities, you're hiding some information, right? You're hiding information about affiliation, or maybe about location here, because GTB is a currency in Nigeria and Naira is a bank in Nigeria. But you're not hiding maybe even the crucial things. So, for example, consider this blue part. This is potentially scary. This is maybe this is about movies. That's what I actually suspect. But this is someone asking about potential criminal offenses, right? The lawyer sharing some details about trials with a family. And we did actually find scary things in wildchat and asked to get this removed. So, for example, there were people polishing contracts between China and Russia in a robotics area. I don't think that was supposed to be shared. Right, so there's a lot of information which could potentially be private, depending on the privacy preferences of people. And if we will remove all this private information, collaboration with remote system will be largely useless, right? So you won't be effectively collaborate. So the good idea from my perspective is to let people decide what they're okay to share and what they absolutely hate to be provided to a big model. So this is how approximately our data looks like. So maybe you can say, I really don't want to share anything about my family things, personal things, but everything about the university maybe except for things from names from recommendation letters I'm spell checking, you can share. Right, so something like this. So it's written in a natural language, expressing preferences about what is shared or not. And by the way, in the data set which we'll discuss, a benchmark, these are generated by some process which involves selecting meaningful attributes and generating them with a LLM naturally, but we are also collecting user data helping us to create profiles which are realistic. So asking what you care about sharing, what you not. So if you have spare 5 minutes, please participate. Okay, so this is a benchmark we created, and this is derived from this wildchat dataset. So wildchat is fairly large. It's close to 1 million of requests. So we used a filtering pipeline to detect information which is potentially private. And we ended up with 15,000, little over 15,000 requests representing different type of private information. And we also created pairing between this request and synthetic privacy profiles in such a way that create kind of interestingly applicable profiles to these examples. The topic distributions is natural, so it's quite skewed. As you would expect, lots of requests in this dataset have to do with editing emails, polishing messages, and so on. But there are also things like generating code. There are parts about translation, medical advice, so it's quite varied. So now the question, how well LLMs will be in sticking to this profile? How can we make them actually respect this? And let's look in a pipeline we use. And this pipeline we played with a different ways. So it's the best version we came up with. If you're basically looking up the paper, there are certain differences. We improved on this since archiving it. And so initially, so you have a small language model and an external language model. So small language model gets a request and gets a user profile. And then it asks to generate a paraphrase, so basically hide information which is private and shouldn't be shared according to the user. And so we have a fairly long prompt explaining how to do this. So we call this agent role as a paraphraser. And then it goes to an agent which is verifying, right? So it's again a local language model which verifies if information which was supposed to be leaked was leaked into this paraphrase. And if it's in this situation, this user didn't want to share their student, and clearly there are lots of markers. So this is probably a hard job for LLM to actually hide this information. Lots of things have to do with being a student. So mentioning lab report, extensions, and supervisor, so you can pretty reliably be sure that's a student. And verifier says, no, I cannot pass this to external model. So this is being processed, then not this original question is being processed by a model, and an answer is provided. Now, if more successful generation happens and verifier lets this pass to external model, then external model creates the answer. And now we have the role of actually providing an answer to the user. It's aggregator takes this role, and it's basically not a simple role, because maybe this original request was oversimplified. Maybe its model, large language model, didn't manage to provide an informative answer, right? So the aggregator needs to figure out to what degree it should rely on the external model. So what initially, when we tell this is a response from big language model, generate your response, the model was actually just reusing this response and hallucinating a lot. So it's really not trivial to get a model to aggregate and think how to integrate new information into this response. So in this case, it was very simple, because all what it was hidden was the flu, so small language model just plugged it in information in the response and provided it to the user. So let's now have a look how well this works. And first, what do we measure? So what we measure a success. And success here is when we are better than external LLM or as good as external LLM. So as good in this case a tie, because we randomize when we use LLM as a judge over the order of generation of external LLM in our system. Right? And so what we measure success, and it's naturally we actually don't expect to improve, right, on external LLMs. That wasn't the goal. So that's why success is being on par, and being on par is good enough. And so what we also have a success of without using this pipeline. So how good small LLM is on itself. So this is certainly we want to improve on. Why would we otherwise collaborated with a big LLM? Okay, so this is success on one side, and leakage is on another side. And we consider two types of leakage, and one is unauthorized leakage. So it's what user said you shouldn't leak, right? So this is what we should be protecting. And basically, what we will want to maximize the success while minimizing this unauthorized leakage. So authorized leakage, actually, it's not something the model should necessarily minimize. It's probably still a good idea for the model not to leak something which is potentially private, but user is kind of relaxed about it, unnecessary. But highly authorized leakage will also be kind of diagnostic tool for us to see that LLM looks in a profile, right? So that actually it relies on the profile to decide what can be passed and what shouldn't be passed. Okay, so first here, this is a little bit of a straw man, to be honest. So this is a Microsoft Presidia system, which is just hiding PI information. So the success rate is kind of decent, but it's leaking like crazy because, of course, it's not aware of the privacy profiles. Now let's look what happens with language models, and we look in local language models, and we look in a range of sizes because, in some sense, you want to have this LLM to be small because it runs on a user side, and maybe user side is not a company but an individual. Or maybe it should even be running on a device, right? But we also look what happens when we have a bigger models as well, open models. Now, this is success of these models on their own. And when we using this system, we can see for most of the systems quite a substantial boost in a success. Not so much for the tiniest Llama 3B because it's actually really bad in performing paraphrasing, in verifying, especially performing paraphrasing. So it's hiding lots of information. So the model should be strong enough to be able to participate in this framework without training. We'll look in training in a bit. They do leak, and you can see that unauthorized leakage from the system varies. And interestingly, the trend is not so straightforward. So you can see that the biggest model, Llama 70B, actually is leaking more than a smaller model, right? It's probably because it's just trying more complex strategies, right? We will look at analysis in a couple of moments. And then you also see that they use rather different strategies about unauthorized leakage. For example, big model understands the profile, understands what can be preserved, right? And that's why unauthorized leakage for the Llama 70B is so high, right? So it's actually capable to understand the task, even so it's not doing it perfectly. Okay, so let's analyze what is happening, because this is a task which is not very natural for models, so they were not really instruction tuned for similar tasks, presumably. So it would be good for us to understand what's going on. And first, a paraphrasing task, and these are results for 8B models. What is happening sometimes is really scary, actually, because sometimes the model misunderstands situation, and actually leaks the privacy profile itself to the external model, saying something, please don't use the information about location of the user, and here is a request, right? And because user doesn't want to share its own location, and still keeping the location itself. So because the task is so unusual, despite us performing prompt optimization, this type of misbehavior is still happening. And it's also overprotecting. Verifier also fails often, so it's not perfect as well. But I think that's also interesting to see what happens with leakage and how leakage differs for different types of privacy information. And some of this is not surprising, because hiding emails, hiding names is very easy. So you expect it to be low leakage. But it seems it's also over-relying on certain preconceptions of large language models. So most large language models seem to think that's OK to share information about children. So if the profile says, don't tell anything about my children, in many cases, the model still preserves this information, even so it seemed like it was fairly easy to remove it. So that was interesting example. So this all together, I think, it motivates this we need to perform fine-tuning of the model, because a model by itself is not performing this task, even bigger models particularly well. So fine-tuning we perform is not particularly exciting, so I'm not going to go into details. So it's as everyone is doing. So there's three different roles here. So one role of paraphraser, one role of verifier, and one role of aggregator. So for paraphrasing, we can use RL or rejection fine-tuning. So select basically generations where the model produced a good output and fine-tune on this, where the whole pipeline produced a good output. And for aggregator and verifier, we basically can perform distillation from a big model. So if we do this, scores improve very substantially. So these are results for 8 B models. So both success and unauthorized leak improve. So success increasing, unauthorized leak is decreasing. But you also see that to achieve the success, it starts to leak more of the things the user was OK to leak. And for reference, these results are actually better than results of 70 B model without fine-tuning. So we can see that moderate-sized models can perform reasonably well. Still, while these scores may look reasonable, of course, it's still quite high leakage. And also, if you look into types, again, leakage of complex types is much higher. So it's, again, not a uniform complexity across different privacy types. So what do we need? Maybe we need more data, or even synthetic data to train this. Or maybe we need a better training algorithms. And I'll use a last minute to mention work not in a safety domain, but I believe the same kind of idea, the same algorithm can be reused in this setting. So in this case, what we are trying to do, we are having a collaboration between VLM, which is pretty good at perception, but not very good at reasoning, with a reasoning model, which in our experiments was DeepSeeker-1. And the tasks we are looking at, the tasks which require substantial reasoning, like mathematical tasks or some analysis of tables. So you need to not only extract information from the image, but also reason over this information. And what you can do, you can fine-tune VLM to produce captions which are informative for the reasoner. So you can do it with a straightforward RL algorithm. So we used GRPO, version GRPO here. But you can see that rewards are fairly sparse, so it will often, it's hard for the model to figure out what actually should go into the caption. So what we do here, during training, we perform an extra clarification dialogue where the reasoner can ask extra questions to the captioner, and we craft also reward in such a way that we actually gives higher reward for finding the solution early on in the dialogue. So in this way, over the time of training, the captioner learns to front-load relevant information in initial caption. So you get now not 0-1 rewards, but a more informative signal for learning. And then at the inference time, you don't use this clarification because it's maybe too expensive, and you still get a strong performance. And similar idea can be used here for training paraphrases, because some ideas, some ways, strategies for paraphrasing the model didn't figure out on its own, and but by performing this type of interaction, I suspect we can improve on this substantially. All right, so this is it for this part as well. So we talked about safety-aware collaboration. And generally, I think we should be thinking about how to create architectures to decentralize the use so that not all the information from the user is flowing to the few entities, and there are many ideas. Of course, creating strong local small, fast LLMs is extremely important, but I don't think that's the only approach, and this is kind of orthogonal to a certain degree. How do you use other LLMs? How do you use other tools without leaking information? In many ways, it's simplified. We look into this question-answer setting, no interaction, no context, no memory about user, and I think there are many exciting problems in here. And this is it for my talk. Maybe just a tiny little plug at the end that in Edinburgh we have this new center of doctoral training, and maybe some people in the audience haven't secured PhD position or know strong people who didn't. So its focuses on responsible NLP, so AI, and safety agents are really something which we want to look into this, and we encourage interdisciplinarity. Thank you very much.
Great. So I think we have time for, sorry, for one question. So anyone who'd like to ask a question, please come up to the mics.
So thank you, Ivan, for the great talk. I had a question related to, your last key messages. One of them you say, training with this approach that you're having can improve. Like, what about when we have like safety critical, or we need clear reasoning? Do you think, going back to the symbolic stuff that I was talking about, do you think these symbolic representations and verification during the chain of reasoning could be an interesting direction to make this to guarantee a bit that some solid reasoning actually happening?
Yes, as Parisa, you probably know, we've done quite a bit of work on narrow-symbolic reasoning, and maybe in certain situations I've seen they didn't deliver on a kind of promises of improved generalization, so it's not always by adding narrow-symbolic reasoning we improve generalization. Sometimes they actually fail miserably, right? Because if you move out of domain too much, so certain type of generalizations, they'll help. For example, we can see if we talk about language recursion as something we can capture if our internal narrow-symbolic reasoning supports this, for example, right? But there are certain limitations. So I think there are domains where this is very important, like safety, where we want to have certain guarantees on the system, right? If you want this to be maybe a system which sticks to certain constitution to certain contracts, what is legal or not. So I'm maybe relating to Bolly stock, right? Or it's also maybe possible to integrate this narrow symbolic scaffold to regularize the model's training, right? So I think right now I'm more trying to push the models where you don't need modifications in architecture, because to have a modification architecture, there is a big overhead. So you need to show substantial improvement from using narrow symbolic backbone, right, for this to have impact, I think.
Okay, thank you. We can maybe discuss
yes,
later offline. Yeah, thank you so
yeah.
much.